Something impossible appeared in the sky on November 2025. Astronomers around the world pointed their telescopes toward a visitor from beyond our solar system, an object called 3I Atlas, and what they saw made absolutely no sense according to everything we know about physics. This was not supposed to exist. The laws of nature that govern how matter behaves in space said this should not be possible. Yet there it was, captured in crystal-clear images that would force scientists everywhere to question everything they thought they understood about comets, space, and the fundamental rules that govern our universe. Imagine you are standing outside in the strongest wind you have ever felt in your entire life. The kind of wind that makes it almost impossible to walk forward, that pushes against you with what feels like invisible hands trying to shove you backward. Now imagine trying to throw a ball backward into that wind against the direction the wind is blowing. The wind would catch that ball immediately and blow it away from you in the same direction the wind is traveling, right? That is exactly what should happen in space when a comet gets close to the sun. The sun creates an enormous wind made of billions upon billions of tiny particles racing outward in all directions at incredible speeds, traveling at approximately 800,000 miles per hour. This solar wind is like a cosmic hurricane that never stops blowing, never rests, pushing everything away from the sun in every direction throughout the entire solar system. When comets approach the sun on their orbits, they begin to heat up as sunlight warms their frozen surfaces and starts releasing trapped gas and dust, creating those beautiful glowing tails that we can sometimes see from Earth streaming behind them across the night sky. But here is the critically important part that every astronomy textbook teaches. Those tails always point away from the sun, always, without exception. The relentless solar wind and the physical pressure from intense sunlight push all the released material away from the sun, exactly like how the wind blows your hair back when you stick your head out of a moving car window. This has been true for every single comet that astronomers have ever studied throughout the entire history of astronomy, until November 2025, when everything changed. On that remarkable day, when scientists captured brand new images of 3I Atlas using advanced telescopes, they discovered something that completely defied every rule in the cosmic playbook that we have built up over centuries of careful observation. The object had not just one tail, but rather multiple tails and jet structures stretching in different directions across space. The primary main tail extended away from the sun exactly as expected by traditional comet physics, reaching an absolutely staggering distance of 2.85 million kilometers into space. To help you truly understand just how enormous and mind-boggling this distance really is, imagine you could drive a car at highway speed without ever stopping to rest. It would take you approximately 3 full years of constant driving, day and night, never sleeping, to travel that far. This single tail stretched across 30 arc minutes of the sky, which is roughly the same width as the full moon appears to us when we look up at night. Think carefully about that for a moment. This was a tail so absolutely massive, so spectacularly huge and unprecedented, that it was 3,000 times larger than the glowing cloud of gas that the famous Hubble Space Telescope had photographed around this same mysterious object just 4 months earlier, back in July 2025. But the truly mysterious discovery, the genuinely physics-breaking observation that has scientists baffled and scrambling for explanations, was what astronomers saw pointing in the completely opposite direction. Two distinct and separate structures were clearly observed extending directly toward the Sun, not away from it. These anti-tail jets stretched outward for 0.95 million kilometers, spanning about 10 arc minutes across the sky. Read that previous sentence again very carefully and let it sink in. Toward the Sun, directly into the solar wind, moving against the enormous pressure of radiation and high-speed particles that should immediately sweep everything away in the opposite direction. Let me give you a helpful comparison to understand exactly why this discovery is so absolutely shocking to the scientific community. Imagine you are standing at the beach on a windy day, standing in the ocean at a spot where powerful waves are constantly crashing against your body. The waves push you back toward the shore with tremendous force that you can feel with every impact. Now imagine looking down and seeing a river of water somehow flowing from the beach, passing through the crashing waves and flowing out into the deeper ocean, water flowing backward through the waves, against them. That would be completely impossible in the real world, correct? The powerful waves would instantly break apart any stream of water trying to flow against them. Yet somehow, impossibly, 3i Atlas was creating solid structures that extended nearly 1 million kilometers toward the Sun, pushing directly into the cosmic hurricane of the solar wind that should rip them apart. Scientists have occasionally seen anti-tails before in other comets over the years, but those observations were always optical illusions caused by viewing geometry. When Earth crosses through the flat plane of a comet's orbit at just the right angle, large heavy dust particles that naturally lag behind the comet in its orbit because of their weight can appear from our perspective to point sunward, even though they are not actually moving that direction. This is purely a geometry trick that depends on where you're standing, similar to how a perfectly straight road can appear to curve and bend depending on your viewing position. These are visual illusions, not real physical structures. But the anti-tail jets of 3i Atlas were completely different from these known illusions. They appeared as clearly defined, sharply organized features with distinct, visible boundaries and consistent structure that remained stable across multiple different observations taken at different times. For these jets to physically exist in reality, for them to maintain their shape and structural integrity while pushing directly through the powerful solar wind, the physics required is almost unbelievable and pushes the limits of what we think is possible. Scientists performed detailed calculations and determined that the material composing these anti-tail jets must be incredibly, extraordinarily dense, far denser than anything normally seen floating in space under typical conditions. The outermost parts of the jets, meaning the sections farthest from the object and most directly exposed to the full force of the solar wind, would absolutely need to have a mass density at least 1 million times greater than the density of the surrounding solar wind itself. 1 million times denser. That is the only possible way the material could physically resist being blown apart into nothing and scattered across space like dust in a storm. Think about the difference between pushing your hand through water versus pushing it through thick honey. Honey is much denser than water, so it flows very differently and holds together much better when disturbed. Now imagine something that is 1,000,000 times denser than the solar wind, somehow being continuously ejected from this mysterious object and managing to hold together in coherent streams across nearly 1,000,000 kilometers of empty space, while being battered by solar radiation. For a completely natural comet behaving normally, the gas that sublimates, which means turns directly from solid ice into gas without becoming liquid first, when heated by intense sunlight, moves relatively slowly compared to other cosmic phenomena. The typical speed is approximately 0.4 kilometers per second, which is roughly equivalent to the speed of sound traveling through hot gas. At that relatively slow ejection speed, for the observed jets to reach their observed lengths of millions of kilometers, the object would need to have been continuously ejecting huge amounts of material for an incredibly long, sustained time period, somewhere between 1 and 3 full months of constant, uninterrupted eruption without stopping. This seemingly impossible situation is what scientists have termed the cohesive jet paradox. How can structures this large, this well-organized, and this remarkably resistant to the hostile solar environment possibly exist according to known physics? The answer that many scientists currently believe connects directly to a catastrophic event that happened to 3I Atlas somewhere near its closest approach to the Sun, a dramatic event we will explore in great detail in the next part of our unfolding story. If the object catastrophically broke apart under stress, violently shattering into many separate pieces or fragments, then each individual fragment would effectively become its own tiny independent comet, with each piece releasing its own personal jet of gas and dust as it heats up. When you have dozens, or possibly even hundreds of these mini-jets, all firing simultaneously in very close proximity to each other in the same region of space, their combined collective effects could potentially create the appearance of massive, highly structured tails and anti-tails. The combined momentum from all these individual jets working together in the same small region of space might generate enough collective pressure to push material even against the powerful solar wind, somehow creating the seemingly impossible structures that shocked astronomers when they first observed them. The magnificent megajets of 3I Atlas represent one of the most visually spectacular and scientifically confusing pieces of evidence in the entire ongoing mystery surrounding this interstellar visitor. They strongly suggest physical forces at work that we do not yet fully understand, unknown processes that directly challenge our carefully constructed models of how comets normally behave when approaching the Sun. Whether these dramatic structures are the unmistakable signature of catastrophic fragmentation, as the majority of scientists currently suspect based on the evidence, or potentially something even more unusual that we have not yet considered, they definitively mark 3I Atlas as an object completely unlike any other celestial body we have ever encountered in the history of astronomy. The scale is absolutely unprecedented. The underlying physics are deeply confounding, and the profound questions these spectacular jets raise lead us directly into the next chapter of this cosmic detective story, where we will discover something even more troubling. we will find that 3I Atlas was not just creating impossible structures in space, it was simultaneously losing matter at an impossible rate, somehow ejecting far more material than should have been physically possible for an object of its estimated size. The mystery only deepens from here, and the mounting evidence becomes even more troubling for scientists trying desperately to explain this mysterious visitor using only conventional science and known physics. The spectacular jets we discovered in the previous chapter were not just beautiful cosmic fireworks. They were clues, fingerprints left behind by something deeply wrong happening to 3I Atlas. When scientists began calculating how much material the object needed to eject, to create those massive structures, they stumbled upon a crisis that threatened to break the fundamental laws of physics. What they discovered was impossible. The numbers simply did not add up. The object was losing more mass than it should have been able to lose. In fact, it was losing more mass than it actually possessed. Let me explain this mystery step by step, because understanding it is crucial to understanding why 3I Atlas has scientists so confused and fascinated at the same time. Remember those enormous jets stretching millions of kilometers through space, pushing against the solar wind with incredible force? Well, to maintain those structures, to keep them from being instantly destroyed by the solar environment, the object needed to be ejecting absolutely enormous amounts of material constantly, month after month. Scientists sat down with their calculators and computers and worked out exactly how much gas and dust would need to be flowing out of 3I Atlas every single day to create what we were observing in our telescopes. The answer they calculated was staggering and deeply troubling. Based on the required pressure to resist the solar wind, based on the observed dimensions and structure of the jets, and based on known physics about how gas and dust behave in space, 3I Atlas was losing approximately 50 billion tons of material every single month. 50 billion tons every month. To help you understand just how much material that represents, imagine every building in a large city, every car, every tree, every person, everything physical you can see around you. Now imagine all of that disappearing into space as gas and dust every few days. That is the scale of mass loss we are talking about here. Now here comes the part where physics breaks down completely. Here is where the crisis emerges that has forced scientists to completely rethink what this object actually is. Before 3I Atlas approached the Sun and started releasing all this material, scientists estimated its total mass based on its size and what we could observe about it from far away. They looked at how it moved through space, how gravity affected it, and how bright it appeared in telescopes. Using all this information together, they calculated that the entire object, the whole thing from core to surface, had an initial total mass of only about 33 billion tons. Read those two numbers again very carefully. The object was calculated to be losing 50 billion tons of material per month, but its entire estimated initial mass was only 33 billion tons total. Do you see the problem? The mathematics here creates an immediate and completely impossible contradiction. The object was losing more material in a single month than its entire body contained at the start. This is like watching someone pour 10 glasses of water out of a pitcher that only held 7 glasses to begin with. It violates the basic conservation of mass. which is one of the most fundamental laws in all of physics. Matter cannot simply appear from nowhere. You cannot lose more than you have. If 3i Atlas truly was a single, solid, unified object, like a giant space rock or iceberg, then what we were observing was physically impossible according to every law of nature we understand. This impossibility forced scientists to search for an explanation, and that search led them to what they now call the fragmentation imperative. The only way the mathematics could work, the only way to resolve this impossible contradiction, was if the object was not actually one piece anymore. It must have broken apart, shattered into multiple fragments, and those fragments were now working together to create the observed mass loss. Think about it like this. Imagine you have a large snowball sitting in the sun. Only the outside surface melts because that is the part exposed to sunlight and heat. The inside stays frozen because the outer layers protect it. Now imagine taking that same snowball and smashing it into 20 smaller pieces. Suddenly, you have 20 different surfaces all exposed to the sun at the same time. The total amount of snow is the same, but now it melts much, much faster because there is so much more surface area being heated. That is exactly what scientists believe happened to 3i Atlas. To understand why this matters so much, we need to talk about how the sun actually causes comets to release material in the first place. When a comet made of ice and rock approaches the sun, sunlight warms up the surface. This heat energy causes the ice to sublimate, which means it transforms directly from solid ice into gas without becoming liquid water first, similar to how dry ice behaves on Earth. This process requires energy, specifically heat energy from the sun. At the distance where 3i Atlas reached its closest point to the sun, called perihelion, the amount of solar energy hitting each square meter of surface was approximately 700 joules per second. That is a fixed amount of energy determined by distance from the sun and the brightness of sunlight. You cannot change it. It is what it is. Now, here is where the thermodynamic crisis becomes unavoidable. To achieve the massive observed sublimation rate of 50 billion tons per month, using only this available solar energy, scientists calculated backwards to figure out how much total surface area would need to be exposed to sunlight. The numbers they got were absolutely shocking. The object would require a total effective absorbing surface area larger than 617 square miles. Let me put that in perspective for you. That is an area roughly equivalent to a single sphere with a diameter of 14.3 miles across. That is enormous. That is the size of a small mountain floating in space. But remember what the Hubble Space Telescope told us back in July 2025 when it captured the sharpest images ever taken of 3i Atlas. Those images showed that the nucleus, the solid core of the object, had to be much, much smaller than that. The upper limit on size that Hubble could measure was only a few miles across at most. When scientists compared the required surface area of 617 square miles against what Hubble actually observed, they discovered something remarkable. The required surface area was at least 16 times larger than what could possibly fit on a single intact object of the observed size. This 16-fold surface area deficit is what scientists now point to as the strongest, most convincing quantitative evidence that 3i Atlas underwent a catastrophic physical event somewhere near its closest approach to the sun. The most likely explanation, the one that makes all the mathematics finally work correctly, is that the nucleus broke apart, possibly violently, shattering into at least 16 separate pieces, and quite possibly many more than that. This breakup event would have dramatically and instantly increased the total surface area exposed to solar radiation. Instead of one object with one surface being heated, you suddenly have 16 or more separate fragments, each with its own surface, each absorbing sunlight, each releasing gas and dust independently. When you account for this fragmentation, suddenly everything makes sense again. The impossible mass loss rate becomes possible because you have multiplied the effective surface area many times over. The enormous jets become explainable because you have multiple sources contributing material to the same structures. The resistance against the solar wind becomes achievable because the combined momentum from many fragments working together can create pressures that a single object never could. The crisis resolves itself, but only if we accept that 3I Atlas is no longer one object, but rather a cloud of debris, a cluster of remnants from what used to be a single interstellar visitor. This conclusion fits perfectly with what we know has happened to other comets in the past throughout the history of solar system observation. Comet Shoemaker-Levy 9, for example, famously broke into more than 20 separate pieces when it passed too close to Jupiter in the early 1990s, torn apart by powerful gravitational tidal forces. Comet Holmes underwent a spectacular explosive outburst in 2007 that increased its brightness by 500,000 times in just 24 hours, likely due to internal fracturing and sudden release of trapped volatile materials. These events prove that violent fragmentation is well within the bounds of natural cometary physics. Comets are fragile objects, loosely held together, and they can break apart when stressed by heat, rotation, or gravitational forces. But here is what makes the potential fragmentation of 3I Atlas particularly interesting and scientifically important. If this interpretation is correct, if the object really did shatter during its journey around the Sun, it suggests something profound about the nature of interstellar bodies compared to comets born in our own solar system. It implies that interstellar objects may be significantly weaker structurally, more fragile, and loosely bound together than the comets we are familiar with from our own cosmic neighborhood. Think about why this might be true. 3I Atlas spent potentially millions or even billions of years traveling through the incredibly cold, nearly empty space between stars. In that environment, there is almost no gravity pulling things together, no warmth to help materials bond or consolidate. The object may have formed as a loose collection of icy materials that barely stuck together, held by the weakest possible forces. Then suddenly, after eons of cold darkness, it plunged into the inner solar system, where it was blasted by intense solar radiation and heated rapidly from nearly absolute zero temperatures to hundreds of degrees within a matter of weeks. That is an enormous thermal shock, similar to taking a frozen glass and plunging it into boiling water. The glass would crack and shatter from the sudden stress. The same thing may have happened to 3I Atlas. Its loosely consolidated internal structure could not handle the rapid thermal expansion and internal pressures created by sudden solar heating, so it fractured and broke apart into multiple pieces. The upcoming observations that scientists have carefully planned for the coming months will be absolutely critical to confirming whether this fragmentation hypothesis is actually correct, or if something else entirely is happening. The object will make its closest approach to Earth on December 19th, 2025, giving us the best possible viewing opportunity with telescopes and instruments here on our planet. Then, on March 16th, 2026, 3I Atlas will pass within 54 million kilometers of Jupiter, close enough for advanced space probes already in the Jovian system to get remarkable views. NASA Juno spacecraft and the European Space Agency, JUICE spacecraft, will both have opportunities to perform high-resolution imaging of the object as it passes by. These observations should definitively answer the critical question: is there still a single consolidated nucleus at the center of all this activity, or has the object fragmented into a cluster of smaller pieces flying in close formation? If telescopes and spacecraft reveal multiple distinct fragments instead of one solid core, then the fragmentation theory will be confirmed and the mass loss paradox will be solved. But if somehow they find a single intact nucleus still holding together, despite everything we have calculated, then scientists will be forced back to their computers and chalkboards to figure out what they are missing, because the alternative explanations become even more extraordinary and difficult to accept within conventional natural science. We have seen how 3I Atlas created impossible structures in space and lost more material than it should have possessed. But there is another mystery surrounding this visitor, one that might be even stranger than the physics we have already explored. This mystery is about the path itself, about the route this object took through our solar system. When scientists carefully traced the orbital trajectory of 3I Atlas and calculated the statistical probability of such a path occurring naturally by random chance, they discovered something that made them question everything all over again. Let me start by explaining what makes this orbit so unusual, so incredibly rare, that some scientists wonder whether it could truly be just an accident of nature. First, you need to understand that objects in our solar system generally move in one of two basic directions around the Sun. Most planets, most asteroids, most comets that belong to our solar system all orbit in the same direction, travelling counterclockwise when viewed from above the north pole of the Sun. This is called prograde motion, and it happens because everything in our solar system formed from the same spinning disk of gas and dust billions of years ago. When that disk was spinning in one direction, everything that formed from it inherited that same direction of motion. But 3I Atlas does not follow this pattern at all. Instead, it travels in what scientists call a retrograde orbit, meaning it moves in the opposite direction compared to almost everything else in the solar system. It is going backward, swimming upstream against the cosmic traffic. Now, retrograde orbits are not completely unknown. Some comets and asteroids in our solar system do travel this way, but they are extremely rare. Only about 1 to 2% of all known objects in the local solar neighborhood have retrograde orbits. Out of every 100 objects astronomers track, only 1 or 2 travel backward like this. That alone makes 3I Atlas unusual, but we are just getting started with the strangeness. The second remarkable feature of this orbit is how perfectly aligned it is with something called the ecliptic plane. The ecliptic plane is like an invisible flat disk that represents the average orbital path of all the major planets in our solar system. Earth, Mars, Jupiter, Saturn, and the other planets all orbit very close to this same flat plane, only tilted by a few degrees at most. When scientists measured the orbital path of 3I Atlas, they discovered something remarkable. The trajectory is aligned with extraordinary precision to this same ecliptic plane, tilted by just 5 degrees from being perfectly flat with it. Think about this carefully for a moment. Space is three-dimensional. An object arriving from interstellar space, from the vast emptiness between stars, could approach our solar system from literally any direction. It could come from above, from below, from any angle in the full sphere of possibilities surrounding us. The chances that it would just happen to arrive aligned almost perfectly with the thin disk where our planet's orbit is incredibly small. Scientists calculated this probability, and the answer they got was shocking. The random probability of such a perfect alignment occurring purely by chance is only about 0.2%. That is roughly 1 chance in 500. Let me give you an analogy to help you understand how unlikely this is. Imagine you are standing in the middle of an enormous empty field that stretches for miles in every direction around you. Now, imagine someone standing at the edge of this field, so far away you can barely see them, throws a frisbee toward you without aiming carefully. What are the chances that the frisbee would arrive perfectly horizontal, exactly parallel to the ground, rather than tilted at some random angle? The chances would be extremely small because there are infinite possible angles it could arrive at, but only one specific angle that is perfectly level with the ground. That is similar to what we are seeing with 3I Atlas, arriving almost perfectly aligned with our planetary plane. But the strangeness does not stop there. When you factor in the other unique physical characteristics of 3I Atlas that we discussed in previous chapters, the massive scale of the object, the unprecedented jets, the extreme mass loss, and combine all of these factors together with the orbital alignment, the combined statistical odds become almost incomprehensibly small. Scientists calculated that the probability of all these features occurring together in a single random natural interstellar object approaches approximately 1 in 100 million. Let me write that number out so you can see it clearly. 1 in 100 million. Those are lottery-winning odds, except much, much worse. This extreme statistical rarity has forced the scientific community into intense debate and soul-searching. Some scientists argue that when something is this improbable, we need to seriously consider that it might not be random at all. They suggest we should investigate alternative explanations beyond standard cometary physics. Other scientists counter that the universe is enormous, containing billions upon billions of objects, and extremely rare events must happen sometimes simply due to the sheer number of opportunities. After all, someone does win the lottery occasionally despite the terrible odds. However, there is a powerful natural explanation for the orbital alignment that many scientists find compelling, and that brings us back to basic galactic dynamics. The statistical calculation showing 1 in 500 odds relies on a critical assumption, specifically that interstellar objects should arrive uniformly from all possible directions in the sky. But this assumption might be fundamentally wrong, because it ignores where 3I Atlas actually came from and the structure of our galaxy. Here is the key insight that changes everything. Our solar system lives inside the Milky Way galaxy, which is not a random blob of stars scattered in all directions. Instead, it is a flat spiral disk, similar to how our solar system itself is a flat disk. Most of the stars, most of the planetary systems, and most of the material in our galaxy exists within this relatively thin galactic disk. The plane of this galactic disk is nearly congruent with, meaning almost aligned with, the ecliptic plane of our solar system. This is not a coincidence. Our solar system formed from material within the galactic disk, so it inherited the disk's orientation. Now think about what this means for interstellar objects. If 3I Atlas was ejected from another star system somewhere within the galactic disk, it would naturally tend to maintain a trajectory roughly aligned with that disk as it travelled through space. When it eventually encountered our solar system, also oriented with the galactic disk, it would arrive moving approximately along the same plane. The alignment is not a miraculous coincidence. It is simply a natural consequence of galactic structure and the fact that most star systems and most interstellar objects originate from within the galactic disk where matter is concentrated. This explanation makes the orbital alignment seem much less mysterious and much more expected. In fact, some scientists now predict that most interstellar objects we detect in the future will show similar alignments with our ecliptic plane, precisely because they originate from the same galactic disk we inhabit. The apparently impossible odds transform into something quite reasonable once we account for where these objects actually come from. But here is where the debate gets really interesting. While the galactic disk explanation works beautifully for the alignment, it does not explain another feature of the trajectory that has captured significant attention. The path of 3I Atlas did not just pass through our solar system randomly, it executed what appear to be strategic flybys of specific planets. The object passed relatively close to Mars during its inbound journey. Now it is heading outward toward a close approach to Jupiter in March 2026, when it will pass within 54 million kilometers of the giant planet. These are not random encounters. The trajectory seems almost designed to interact with the solar system's primary bodies in sequence. From one perspective, this could simply be coincidence. The solar system contains 8 major planets spread across its ecliptic plane, so any object travelling along that plane has a decent chance of passing near at least 1 or 2 planets purely by accident. But, from another perspective, the sequence of encounters looks suspiciously like a carefully planned route, the kind of trajectory that a spacecraft might follow if it were designed to survey multiple planets during a single pass through an alien star system. This is where the statistical improbability transforms from being merely a curiosity into something that suggests possible deliberate intent, at least to those scientists willing to consider non-natural explanations. The trajectory analysis reveals something else important that connects back to our earlier discussion about the object's possible origins. When scientists broke down the velocity of 3I Atlas into components, measuring how it moves through the galaxy, they discovered that it has an unusually high vertical velocity component. This means it is not just travelling within the flat plane of the galactic disk. Instead, it is moving upward through that plane at a significant speed, about 18.5 kilometers per second relative to the Sun in the vertical direction. This high vertical velocity suggests the object belongs to what astronomers call either the thin disk or thick disk populations of the galaxy, groups of stars and objects that have tilted orbits carrying them above and below the main galactic plane. The thick disk population is particularly interesting because it consists mainly of older stars, stars that formed billions of years ago when the galaxy was younger and had a different chemical composition than it does today. If 3I Atlas originated from a planetary system orbiting one of these ancient thick disk stars, it could potentially be billions of years old, perhaps even older than our own solar system. This would make it not just an interstellar visitor, but a genuine time capsule, carrying material and chemistry from an earlier epoch of galactic history. Understanding the true origin of 3I Atlas requires more than just calculating probabilities. It requires understanding the complex dynamics of how objects move through the galaxy, how planetary systems form and evolve, and how material can be ejected from one star system and captured or encountered by another across vast interstellar distances. The orbital geometry, as strange and improbable as it initially appears, provides crucial clues about this object's history, its age, and the environment where it formed. Whether that geometry represents pure chance, natural galactic dynamics, or something more purposeful, remains one of the central questions driving ongoing research and observation. As we continue to observe 3I Atlas during its departure from our solar system over the coming months, tracking its exact path and measuring any tiny deviations from predicted trajectories will help scientists distinguish between these competing explanations. But the orbital puzzle is only one piece of a larger mystery. As we will see in the next chapter, the chemical composition and physical properties of this object reveal anomalies just as profound and puzzling as its impossible jets, paradoxical mass loss, and statistically improbable path. We have explored the impossible jets, the paradoxical mass loss, and the statistically improbable orbit of 3I Atlas. Now we turn to perhaps the most revealing clue of all, the actual chemical makeup and physical properties of this mysterious visitor. When scientists pointed their most sophisticated instruments at the object and analyzed the light coming from its glowing cloud of gas and dust, they discovered a composition profile so unusual, so radically different from normal comets, that it suggests this object formed in an environment completely alien to anything in our solar system. The chemistry of 3I Atlas tells a story of exotic origins, extreme conditions, and perhaps billions of years of transformation in the cold darkness between stars. Let me start with the most basic question astronomers ask when they discover a new comet. What is it made of? To answer this, scientists use powerful telescopes equipped with instruments called spectrographs that split light into its component colors, similar to how a prism creates a rainbow. Each chemical element and molecule produces a unique pattern of bright and dark lines in this rainbow of colors, like a fingerprint that identifies exactly what substances are present in the comet's atmosphere. When scientists analyze the spectrum of light from 3I Atlas using instruments on the James Webb Space Telescope and other advanced observatories, they found something remarkable and deeply puzzling. The cloud of gas surrounding 3I Atlas, called the coma, is absolutely dominated by carbon dioxide. This is the same gas that we breathe out, the same gas that makes soda fizzy, but in this case it represents the primary volatile material, being released as the object heats up near the sun. Now, carbon dioxide is not unusual in comets by itself. Many comets contain some carbon dioxide ice mixed with other materials. But what makes 3I Atlas extraordinary is the ratio. Scientists estimate that the object contains only about 4% water ice by mass. 4%. Let me put that in perspective for you. Most comets from our own solar system are made primarily of water ice, typically somewhere between 50 to 90% water. Water is usually the dominant ice, the main ingredient, with everything else being minor additions. But 3I Atlas flips this completely backward. It is almost entirely carbon dioxide, with just a tiny bit of water mixed in. This extreme composition makes 3I Atlas a massive outlier, an object that does not fit the normal patterns we see in solar system comets at all. Think about it like this. Imagine you went to a beach and started examining sand. You would expect to find mostly quartz grains with maybe some shells and rock fragments mixed in. But then, imagine finding a bucket of sand that was 95% shells and only 5% actual sand grains. You would immediately know something unusual happened to create that mixture, that it formed under very different conditions than normal beach sand. That is exactly what scientists are seeing with the composition of 3I Atlas. The dominance of carbon dioxide over water tells us something profound about where and how this object formed. Carbon dioxide freezes at a much lower temperature than water. For carbon dioxide to be the main ice while water remains rare, the object must have formed in an extraordinarily cold environment, colder than the regions where our solar system's comets typically originate. This suggests 3I Atlas might have formed far from its parent star, perhaps in the frozen outer reaches of an alien planetary system, or possibly in the frigid depths of interstellar space itself, where temperatures hover just a few degrees above absolute zero. But the chemical mysteries do not stop with the unusual ice composition. The truly perplexing discovery came when scientists detected the presence of metallic elements in the gas cloud, specifically nickel and iron. These heavy metal atoms appeared in the spectroscopic data at surprisingly high abundances, creating what scientists call an extreme abundance ratio. Now, here is why this is so chemically puzzling and difficult to explain. Metals like nickel and iron have incredibly high melting and boiling points. Iron does not turn into vapor until you heat it to about 2,862 degrees Celsius. Nickel requires similar extreme temperatures. The problem is that 3I Atlas, even at its closest approach to the Sun, never got anywhere near hot enough to vaporize solid metal particles. Think about what this means. The object is releasing metallic vapor into space, but it is not hot enough for that vapor to exist, according to normal physics. So, where are these metal atoms coming from? Scientists have proposed several possible explanations, but none of them are completely satisfying. One hypothesis is that the object might be intrinsically metal-rich, meaning it contains an unusually high concentration of tiny metallic grains mixed throughout its icy material. When the ice sublimates and rushes away from the nucleus, it might drag these tiny metal particles along and somehow break them down into individual atoms through collisions and friction. Another possibility is that internal chemical reactions happening inside the object, reactions we do not fully understand. somehow produce metallic vapor at much lower temperatures than should normally be possible. For those scientists investigating the possibility of non-natural origins for 3I Atlas, these abundant metal ratios raise a particularly intriguing question. Could the detected nickel and iron represent industrial alloys, artificially produced materials that would not occur naturally in such proportions? While this remains highly speculative and is not accepted by the mainstream scientific community, it demonstrates just how unusual and difficult to explain the observed chemistry really is. The presence of metals in quantities that defy straightforward thermal explanation adds another layer to the mounting mystery surrounding this object. Beyond chemistry, 3I Atlas presents another unique physical signature that has astronomers scratching their heads. The object exhibits what scientists call extreme negative polarization. In the light, it reflects back toward Earth. To understand what this means, you need to know a little bit about how light behaves. Normal sunlight vibrates in all different directions as it travels through space. When that light bounces off an object and comes back to us, the surface properties of that object can cause the reflected light to vibrate preferentially in certain directions rather than others. This is called polarization, and measuring it tells scientists important information about the size, shape, and composition of the particles on the object's surface. The specific type of negative polarization that 3I Atlas displays at small viewing angles, meaning when we observe it from certain positions, is physically unprecedented. This exact light scattering signature has never been seen before in any known comet or asteroid in our entire catalogue of solar system objects. The measurement is so unusual that it effectively classifies 3I Atlas as belonging to a previously completely unobserved population of bodies. It is not just different in degree. It is different in kind, exhibiting optical properties that suggest its surface materials or particle structures are fundamentally unlike anything we have encountered before. Now, here is where all these compositional and optical anomalies might actually connect together into a single coherent explanation rooted in the object's extraordinary history. Remember that 3I Atlas has been traveling through interstellar space for potentially billions of years, based on the orbital analysis we discussed in the previous chapter. During that immense journey through the vast emptiness between stars, the object has been continuously exposed to something called galactic cosmic rays. These are high-energy particles, mostly protons and atomic nuclei, that zoom through space at nearly the speed of light. They are far more intense and energetic than the solar wind we experience here in our relatively protected solar neighborhood. When these cosmic rays slam into the surface of an icy object over millions and billions of years, they cause profound chemical changes through a process called radiation processing. The high-energy impacts break apart molecules, create new chemical bonds, produce exotic compounds that would never form under normal conditions, and fundamentally alter both the volatile ices and the rocky refractory materials in the outer layers. This bombardment can create complex organic molecules, change the structure of ice crystals, darken surfaces, and produce unusual mixtures of materials that have no equivalent in objects that spent their entire lives sheltered within a planetary system. This intense radiation history could potentially explain all three major compositional anomalies we observe. The unusual ratio of carbon dioxide to water might result from preferential destruction of water molecules by cosmic rays, or from chemical reactions that converted water into other compounds over eons of bombardment. The presence of metallic vapors at low temperatures might be explained by radiation creating unusual chemical pathways or loosely bound metal compounds that release vapor more easily than pure metals would. The extreme negative polarization signature could reflect unique surface properties produced by billions of years of radiation processing, creating particle structures and material mixtures that simply do not exist on solar system objects that never experienced such exposure. If this interpretation is correct, then 3I Atlas is far more than just a visitor from another star system. It is a genuine cosmic time capsule and messenger, carrying within its altered structure preserved clues about the formation chemistry of planetary systems that existed billions of years ago in regions of our galaxy far removed from our Sun. The exotic composition we observe is not necessarily how the object looked when it first formed. Instead, it represents the cumulative result of an almost incomprehensibly long journey through the harsh radiation environment of interstellar space, a journey that transformed its chemistry and physics into something alien to our experience. This makes studying 3I Atlas extraordinarily valuable scientifically, because it gives us a window into processes and conditions we can never observe directly. We cannot travel to other star systems to sample their comets. We cannot recreate billions of years of cosmic ray exposure in our laboratories. But we can study this visitor that has done that journey naturally and brought the results directly to our telescopes. Every spectrum we take, every measurement we make, helps us understand not just this one object, but the broader processes of how matter evolves and transforms during the long, dark ages between stars. The compositional analysis reveals that 3I Atlas is profoundly, fundamentally different from the comets born in our own Oort cloud or Kuiper belt. Whether these differences arise purely from natural radiation processing during an extended interstellar voyage, or whether they hint at something even more unusual about the object's origins and nature, remains an open question that will drive observations and analysis for months and years to come. As we will see in the next chapter, these chemical and physical anomalies take on additional significance when we compare 3I Atlas to the only other major interstellar visitor we have studied in detail, an object that presented its own unique mysteries and sparked intense debate about the possibility of artificial origins. We have now explored 4 major mysteries surrounding 3I Atlas: the impossible jets that defy solar wind physics, the paradoxical mass loss that violates conservation of matter, the statistically improbable orbital alignment, the exotic chemical composition unlike anything in our solar system. Each anomaly by itself might be explained away as unusual but still natural. But when you stack them all together, when you consider the full picture of everything strange about this object, some scientists begin to ask a question that sounds like science fiction, but demands serious consideration. Could this visitor be something other than a natural comet? Could it possibly be artificial, designed and built by intelligent beings from another star system? Before you dismiss this idea as crazy, before you laugh and say that sounds impossible, consider what we have already learned about interstellar visitors to our solar system. 3I Atlas is not the first mysterious object from beyond our Sun to raise questions about artificial origins. In fact, it is the third confirmed interstellar object we have ever detected, and each of the three has presented its own unique puzzles that challenged our understanding. To truly appreciate the debate surrounding 3I Atlas, we need to compare it to the visitor that came before and started this entire conversation about the possibility of interstellar technology. We need to talk about one, Oumuamua. Oumuamua arrived in October 2017, detected by the Pan-STARRS telescope in Hawaii, as it was already leaving our solar system after swinging around the Sun. The name means scout or messenger in Hawaiian, and it earned that name by being the very first object astronomers confirmed definitely came from interstellar space based on its trajectory. But Oumuamua was strange from the very beginning, exhibiting properties that did not fit any category of object we had seen before. It was small, probably only about 100 meters long, shaped like a cigar or perhaps a flat pancake, depending on which analysis you believe. It tumbled wildly as it moved, rotating every 7 to 8 hours. It showed absolutely no signs of cometary activity, no tail, no visible coma of gas and dust, appearing completely inert and dead like an asteroid. Yet despite appearing inactive, Oumuamua exhibited clear non-gravitational acceleration, meaning it was speeding up in ways that could not be explained by the Sun's gravity alone. Something was pushing it, giving it an extra boost as it travelled. For a normal comet, this acceleration would be easy to explain. Comets naturally accelerate when gas sublimates from their surfaces and shoots out like tiny rocket engines, creating thrust. But Oumuamua showed no evidence of releasing any gas at all, no visible outgassing that could account for the observed acceleration. This created a genuine scientific mystery. What was pushing Oumuamua if not cometary jets? This puzzle led Harvard astronomer Avi Loeb and several colleagues to propose a controversial hypothesis. What if Oumuamua was not a natural object at all, but rather an artificial light sail, a thin reflective sheet designed to be pushed by radiation pressure from starlight? A light sail made of extremely thin material, perhaps just a few millimeters thick, would be so lightweight that even the gentle pressure from sunlight could accelerate it noticeably, explaining the observed non-gravitational motion without requiring any visible gas emissions. The hypothesis was mathematically consistent with observations and could not be definitively ruled out by available data. Though most scientists remained skeptical and preferred to believe that Oumuamua was simply an unusual comet, made of materials that sublimate without producing visible dust clouds. Now contrast that story with what we are observing from 3I Atlas. Where Oumuamua was tiny and inactive, 3I Atlas is enormous and spectacularly active. Where Oumuamua showed no visible coma or tail, 3I Atlas displays jets extending millions of kilometers. Where Oumuamua was estimated to have a mass of perhaps a few million kilograms at most, 3I Atlas has an estimated mass of tens of billions of tons, making it literally millions of times more massive. The two objects represent completely opposite extremes of the interstellar visitor spectrum. They could not be more different from each other in terms of size, activity level, and observable behavior. This difference is critically important because it means the light sail hypothesis that might have worked for Oumuamua cannot possibly work for 3I Atlas. You cannot build a light sail out of an object containing 33 billion tons of material. It would be far too heavy for radiation pressure to move significantly. The object is simply too massive for that explanation to make any physical sense. So if we are going to seriously consider a non-natural origin for 3I Atlas, if we are going to explore the possibility that it might be artificial, we need a completely different technological explanation than the one proposed for Oumuamua. We need to think about propulsion systems that can move massive objects through space. This is where the mass paradox we explored in Part 2 takes on additional significance beyond just the fragmentation hypothesis. Remember that natural cometary propulsion through sublimation is thermodynamically very inefficient at moving objects through space. When ice turns into gas and escapes from a comet, that gas moves relatively slowly, at only about 0.4 kilometers per second, which is roughly the speed of sound in hot vapor. Because the exhaust velocity is so low, you need to eject absolutely enormous amounts of material to generate significant thrust or to change the object's trajectory noticeably. This is why the calculated mass loss rate of 50 billion tons per month seemed so impossible. Natural sublimation is just not an efficient rocket engine. But what if the jets we observed were not natural sublimation at all? What if they represented technological thrusters, artificial propulsion systems deliberately designed to maneuver the object? Here is where the physics becomes fascinating. Technological thrusters can achieve vastly higher exhaust velocities than natural gas sublimation. Even relatively simple chemical rockets, like the ones we use to launch satellites into orbit, can achieve exhaust speeds of 3 to 5 kilometers per second, which is roughly 10 times faster than natural cometary outgassing. More advanced propulsion technologies that humans have already developed, like ion thrusters that accelerate electrically charged particles using electromagnetic fields, can reach exhaust speeds of up to 50 kilometers per second, or even higher, more than 100 times faster than sublimating ice. Now here is the critical insight. The amount of material you need to eject to produce a given amount of thrust depends directly on the exhaust velocity. If you double the exhaust speed, you can cut the required mass flow rate in half, while still producing the same force. If you increase exhaust speed by a factor of 100, you can reduce the required propellant consumption by a factor of 100. This means that high-efficiency thrusters could potentially generate the observed powerful collimated jets and any detected non-gravitational acceleration using only a tiny fraction of the material that would be required by natural sublimation. Instead of needing to eject 50 billion tons per month, an advanced propulsion system might need to consume only a few 100 million tons, or even less, easily allowing 3I Atlas to remain intact as a single body throughout its entire passage through our solar system. This efficiency disparity forms the critical dividing line in the current scientific debate about the nature of 3I Atlas. On one side, the overwhelming majority of scientists firmly favor the natural explanation we discussed in Part 2. They believe the object catastrophically fragmented near perihelion, breaking into at least 16 pieces and quite possibly many more, thereby multiplying the effective surface area and making the observed high mass loss rate physically possible using only natural solar heating and ice sublimation. This explanation requires no new physics. invokes no unknown processes, and fits within our established understanding of how comets behave when stressed by thermal shock and internal pressure. On the other side, a much smaller but vocal group of scientists, including Avi Loeb, who previously advocated for reconsidering Oumuamua, argue that the statistical improbabilities and extreme physical anomalies we have discussed throughout this story should compel us to at least seriously investigate the possibility of technological origins. They point out that science advances by considering unlikely explanations when conventional theories struggle to account for all observations. They emphasize that what they call black swan events, occurrences so rare and unexpected that they fall outside normal statistical distributions, do happen in nature and in the universe, and that dismissing possibilities simply because they seem improbable can blind us to genuine discoveries. From this perspective, the extraordinary size of 3I Atlas takes on special meaning. If this object truly were an artificial construct, a spacecraft or probe built by an advanced extraterrestrial civilization, its enormous scale would suggest that its creators possessed engineering capabilities far exceeding anything humans have achieved or even seriously contemplated. We are talking about an object potentially several kilometers across, containing tens of billions of tons of material, somehow propelled across interstellar distances and maneuvered precisely through our solar system. The level of technology required to accomplish such a feat would be almost incomprehensibly advanced compared to our current capabilities, placing its builders somewhere on what scientists call the Kardashev scale, at a level far above our own civilization. The scientific consensus at this moment in November 2025, based on all available evidence and observations, strongly favors the natural fragmentation hypothesis. Most astronomers and planetary scientists believe that 3I Atlas is indeed a comet, albeit an extremely unusual one, with exotic composition resulting from billions of years of cosmic ray processing during its interstellar journey, that broke apart due to thermal stress when it approached the Sun. The chemistry we observe, the carbon dioxide dominance, the metal abundances, the unusual polarization, all of these can be explained, though not always easily, through natural processes acting on material that formed in an alien stellar system under conditions different from our own solar nebula.